Hello students, it's Mr. Bornheimer, and I'm just going to go ahead and kind of give you a brief example of a thermochemical equation. Okay, so the one that I'm going to give an example of, you may have seen it in class, is kind of this idea of the combustion of propane. However, I thought it might be more interesting if we kind of switched it up a little bit and instead of use propane, used methane. So I know, another hydrocarbon, but you know, combustion is my favorite. So here we go. Alright, so we're going to go ahead and write the chemical reaction for the combustion of methane. And if you remember your alkanes, you know, your meth, eth, prop, bute, okay, methane is going to be 1C. And if it's combustion, it's going to be combined with O2. And we see that in almost every combustion of every hydrocarbon, we have the production of H2O and CO2. Okay, so we see this kind of happening here. Now, the next thing that we really want to focus in on is balancing this chemical equation. Just like in stoichiometry, balancing chemical equation is going to be absolutely crucial. So, we're going to go ahead and balance this. There's 1C over here, and there's 1C over here. So in the C's we're good. There are 4 H's here. There are 2 H's here. So it might be to our benefit to go ahead and put a 2 here in front of the H2 just to get it to balance. Okay, made a change, but I didn't make a change to the carbon, so for the most part I'm good. And now it's time to add up all our oxygens. So we have 2 oxygens here. However, we have 2 oxygens over here because of the 2, and we have 2 oxygens here. So what we see happen is that this, we're going to have to put a 2 here in front of the O2, and now we have 4 oxygens on both sides. So the final form of our equation is going to be CH4 plus 2O2 reacts to produce 2H2O and CO2. Okay, and this is going to be our equation. Now this is not a thermochemical equation yet because we haven't actually looked at the energy associated with this reaction yet. So right now it's just a plain old chemical reaction. Okay, so what I'm going to do is I'm going to go ahead and kind of select this object. Okay, or I'm actually just going to move it up here, and we're going to go ahead and look at it in depth. So actually, I want to work on adding energy to this equation. So we're going to do that here. Okay. And I'm going to tell you that the energy that's associated with this, the energy associated with this chemical reaction is a negative 64 kilo, oh, Mr. Bornheimer's bad, not kilograms. Okay. I want to go ahead and get rid of, I'll just rewrite that. A negative 64 kilojoules is what we're dealing with here. And it is negative because we're dealing with an exothermic reaction, okay? And it's exothermic because energy is being expelled. Remember, this is combustion. It's going to produce heat in the sense that we're going to feel warm air, okay, and light, which is also energy. Okay, it's energy that's being expelled in the form of light. So we know that this reaction is exothermic because that means that energy is exiting our system. We would say that it is leaving, it is negative, it is no longer in our system. The system being just these chemicals here, so therefore it is negative. So negative 64 kilojoules are leaving our system. Okay, let's go ahead and add another page to that. Alright, so we know that our delta H is a negative 64 kilojoules. And this means that that energy is leaving. But that is the energy that leaves, okay, for every mole of CH4. And that is the energy that is released when we use, okay, 2 moles of oxygen. Notice that these numbers here, okay, these numbers, the 1 and the 2, these numbers are associated with the chemical reaction, okay? So the 2 and the 1, they're associated with the coefficient in the chemical reaction. For every 1 mole of methane and 2 moles of oxygen, 64 moles of kilojoules of energy, not moles, excuse me, 64 kilojoules of energy is going to leave. But what happens if I started with 3 moles of propane? Okay. Well, there is no 3 in front of the chemical reaction, but we know, based on this information above, that for every 1 mole of methane, 64 kilojoules is released. So we can actually use this to our advantage. Okay? We can actually go ahead and multiply this, and we actually end up with what? 3 times 60 is, make a guess, 180. And 3 times 4 is, make a guess, 12. And if we add 180 and we add 12, we get 194 kilojoules of energy released when 3 moles of methane is combusted. Now, I chose 64, so a little disclaimer here, I chose 64 kilojoules. That is not the actual amount of energy released for this particular chemical reaction, but you can look up the amount of heat that is released when methane is combusted. Okay, so this right here is kind of how you solve thermochemical equations, and this here, okay, is what we call our thermochemical conversion factor for this chemical reaction, where we take and we put the energy on top. We put the energy on top here, and we put the moles that it corresponds to and the particular chemical it corresponds to from the chemical reaction in the bottom. And what the benefit of this is that the moles cancel out and we're left with kilojoules, and we see that right here. Okay. Hopefully this little tidbit helped you. If you have any further questions, you can go ahead and contact me. Otherwise, thank you for watching and have a great day.